Example 3. Given the parabola y is equal to x squared, find the average rate of change of y with respect to x at the interval from 2 to 5. Second is to find the slope of the parabola at the point P 2, 4. Then you have to write an equation for the tangent to the parabola. Okay, so remember in the first problem, you're asked to find the average rate of change. So that's the slope of the line secant to the curve over the interval from 2 to 5. And then if you look at the slope of the parabola at the point, that's going to be the slope of the line tangent. And we're going to write an equation for the tangent to the parabola. So this is how it looks like. We have a parabola. And so over the interval from 2 to 5. Okay, so if this is from 2 to 5, your y would be 4 here, and your y when x is equal to 5 is 25. Obviously, this is not to scale, but this will do. Okay, so the secant line would have a slope equal to delta y over delta x. So that's y of 5 minus y of 2 over 5 minus 2. So that will be equal to 5 squared minus 2 squared over 3. So that's 25 minus 4, so 21 over 3. You have 7. So the slope of this line secant to the curve y is equal to x squared would have a slope equal to 7. Next, find the slope of the parabola at the point P of 2, 4. Write an equation for the tangent to the parabola. So in order to solve this problem, we have to look at our original function y is equal to x squared, get the derivative, which is 2x. Then the slope of the line tangent to the curve at the point when x is equal to 2 would be f prime of 2, that is y prime of 2. So that's 2 times 2, which you substitute x equal to 2 here, so you get 4. So the slope of the line tangent to the curve at x equal to 2 is 4. Okay, and now we're not done yet. So we've got the slope, so now we use the slope point form. Okay, to find the equation of the tangent line. So y minus y1 is equal to m times x minus x1. So our x1 and y1 would then be 2, 4. So this is y minus 4 equals, the slope would be 4 times x minus 2. So that's equal to y is equal to 4x minus 8, and you move that to the other side. So y is equal to 4x minus 4. So this is the slope, this is the equation of the line tangent to the parabola. So if you notice here, let's go back to the previous slide. Okay, so here, if you look at the line tangent to the curve at 2, you're going to have something like this. Okay, so this line would have this, the slope of the secant line is 7, while the slope of the tangent line is 4, which you can tell that it has a lower slope than the secant line. Okay, pardon my line is looking so crude, the tangent line. Okay, what is the slope of the line tangent to the parabola y equal to x at any point? Well, that means if it's any line, since y prime would be 2x, right? So the slope at any point would be 2 times x of 0. Okay. Example 4. What is the rate of change of the area of a circle with respect to the diameter when the diameter is 10 meters? Right? So whenever it's an instantaneous rate of change of a function, you have to make sure that it has to be at a particular unit, or a particular x, or particular d, particular time. Okay, so what would be how do we formulate this problem? How do we even solve this? Now it talks about the area, and it's with respect to the diameter. Okay, well, that means let's look at the area first. Area we know is pi r squared. But then we're looking at the diameter. So remember, twice of the radius is the diameter. So r would be d over 2. Okay? So now we have to define this as a of d. That's the function. Pi, replace the r by d over 2 squared. So what you've got is a pi d squared. Let me put the 2 right here, as that's squared over 4. Okay, so now what is the rate of change at a particular diameter? So a prime of d would be 2 pi is a constant d, so you are differentiating with respect to d. So bring down the power 2, and that's why you have d over 4. So if we want to rewrite this pi over 2d. So this is your derivative function for the rate of change of the area of a circle with respect to the diameter. So then when it's asked, what is it at the instant when? Okay, so when d is equal to 10, what we've got would be a prime of 10, which is equal to pi over 2 times 10, so that's going to be 5 pi. Okay? Motion along a line. Let's talk about displacement, velocity, speed, acceleration, and jerk. Okay, suppose we have an object that is moving along the coordinate line, so this is your s-axis right here. Okay? Usually horizontal, it could be vertical, so that we know its position s on the line as a function of time. That means this is the position as a function of time. Okay, so the displacement of the object over the time from t up to, say, t plus delta t. So it could be h, that's the same as h, or it could be delta x. So that's just change. The displacement is just how much distance is it traveled, basically. Okay, so f of t plus delta t minus f of t. So say this is its position at t plus delta t. So there's your f of t plus delta t, and this is your position s, which is also defined as f of t. So what is the displacement? It's just the change in position. Okay, so it's delta s, which, as you can see, it's just the change in position. All right? Okay, now what is the average velocity? The average velocity of the object over the time interval is the same thing. It's just delta s over delta t, displacement over the time elapsed. All right? So it's f of t plus delta t minus f of t over delta t. Now, when we talk about, so this is the average. So we have another definition. When we talk about velocity, or it's the instantaneous velocity. So in physics, especially if you're looking at word problems in physics, usually they just say that velocity. It's the derivative of the position function with respect to time. So if a body's position is s equal to f of t, then the velocity is just the derivative with respect to time, and that's just the slope of the secant line, and you let delta t go to 0, then it becomes the slope of the line tangent. Okay? The speed is just the absolute value of the velocity, because the velocity could be positive or negative, which determines the direction of the particle moving, or the object that's moving. Okay? Right. So figures 3.13, for motion S along a straight line, when S is increasing, that means it's changing its position. So let's say this is the distance traveled, and then it's moving in this position. These are the different positions over the interval time. If you look at this, the slopes of the lines tangent to every point of the curve f of t, then we know that its velocity is positive, okay, because ds by dt is positive. Now, if you start off at this position and then you're decreasing, then the velocity would be negative, okay, because it's moving downward. This is, by the way, this does not portray the pathway. It's the distance traveled over time. Okay, that's not the path of the motion of the particle or an object. Okay?